Hello everyone, my name is Hunter McDaniel. I'm the founder and CEO of UbiQD, and we're an advanced materials company powering product innovation in energy. And I'm very excited to be giving you this presentation today virtually for the 20th anniversary of the International Meeting on Information Display in South Korea. And I would have loved to be there in person. Unfortunately, it wasn't possible this year, but hopefully next year I can join you. I'd like to start by acknowledging the National Science Foundation as one of the primary sponsors of the work that I'm going to be talking about today via the Small Business Innovation and Research Program in the United States. So when I say powering product innovations in energy, I mean that we're doing that with quantum dots. They're an enabling material that really can give you new functionality in products, in particular in energy. And I think most of you are familiar with what quantum dots are, but briefly, they're tiny nanoparticles of semiconductor that are highly efficient at manipulating light using photoluminescence. And our proprietary quantum dots are safer, cheaper, and more stable than competitors, which enable them to be used in even more applications, and in particular in large area sunlight exposed applications. And I think many of you are quite familiar with quantum dots. Historically, there are some challenges there, in particular with toxicity. The old school quantum dot was cadmium selenide, or if you wanted to go into the infrared, you would use lead sulfide. More recently, indium phosphide has become popular, for example, in a host of different TV products that are on the market today use indium phosphide quantum dots. In all of these cases, the quantum dots are hazardous, in some of these cases highly expensive, cost intensive, and have reliability issues, which ties into the cost, because if you have something that's not air stable, you have to spend more cost on encapsulation. And so again, this has made them historically inadequate or unsafe to use in non-display applications. Now, I think several of you might be thinking that it's controversial to say that indium phosphide is toxic. So I just wanted to have a quick slide on that. It actually is highly toxic, and there's been a number of papers published and studies done showing the toxicity of indium phosphide. The National Institute of Health had a 3-year study on rats and mice showing that it caused cancer. And we've done some studies ourselves comparing our quantum dots to cadmium-based and indium phosphide-based quantum dots with Los Alamos National Laboratory. This work has been submitted for publication, is under review now, but one of the key takeaways was that the cell viability at a high concentration, roughly 100 micrograms per milliliter, after 6 days was essentially 100% for all of the forms of our quantum dots, variety of peak emissions and actually ligands, even when we had selenium, which we sometimes alloy in to extend the emission wavelength. Whereas with cadmium-based materials, between roughly 25 and 50% of the cells remained. So roughly 75% or so of the cells were dead. And then indium phosphide was even worse. Depending on the supplier, we saw almost complete cell death with indium phosphide quantum dots under the same apples to apples study. We also looked at gene expression, and we found that the indium phosphide quantum dots were associated with, they had upregulated genes associated with apoptosis, which is a gene that is related to cell death as well. So it really shouldn't be surprising given the fact that the phosphine precursors that are often used are also used in fumigation for pests, to remove pests. And it's well known that phosphides can form phosgene in the digestive system. So actually zinc phosphide is frequently used as rat poison. So don't mean to throw indium phosphide too much under the bus, but just to make sure that we're getting our facts straight about the toxicity of this cadmium-free material, in some cases more toxic than the cadmium-containing materials. So our materials are based off of copper indium sulfide, and sometimes we do copper indium selenide if we want to tune that emission. Very similar otherwise. We do a core shell structure. We have numerous patents and trade secrets related to this compound. We can get high quantum yield near unity, consistently above 95% through the visible and the near infrared. And we have a very low cost manufacturing process. You can see one of our smaller reactors there on the left. which would produce about 1.5 kilos of material per batch, which would be enough for about 5,000 square feet or so of windows or film. And I wanted to highlight that we do make these materials available for research, and you can purchase them on Strim, strim.com. You can find a whole host of the different peak emissions that we manufacture there, if you'd like to purchase and try them out. Given that this is a display conference, I won't be focusing on display, as there are other leaders in the industry doing quantum dots for display. And Nanosis is, I would say, #1 in that regard. But I wanted to highlight that we have a recently announced partnership with Nanosis. As the undisputed leader in quantum dot manufacturing and display technology, they can bring a lot to the table in terms of scale and economies of scale to basically get costs down. And also in terms of manufacturing technology and polymer technology. So the agreement that we have with Nanosis is to basically set them up to help us manufacture larger quantities of quantum dots, of our quantum dots. But we're also working with them on developing new quantum dot nanocomposites, polymer composites. And so we're very excited about this. You can see this picture on the right where one of their researchers is holding some of our film that we use in greenhouses, and behind him you can see a 1,200 liter reactor. If you'd like to learn more about that, just do a search online. You'll see some announcements and press that covered this new partnership. Okay, so the heart of my talk is really around energy and our technology relating to windows. And so I'm going to start off here giving a little bit of motivation for that technology and the work that we've done there, and then get into some specifics. And I'll have some very fresh data that I don't think anyone else has seen publicly. It's about to be published, so you're getting a first view of some recent results. Okay, first with the motivation. So we're very passionate about solving energy problems, and it's largely due to climate change. I think it's undisputed that man is having an effect on the planet's climate in a negative way. The increase in carbon dioxide content in the atmosphere is being strongly correlated with the rise in temperatures globally. And we've seen the consequences of this in many different ways, which I won't get into here, other than to say that it's really a problem that we rely so heavily on carbon dioxide releasing technologies that are causing harm to the environment, but also existential risk to the human race. And so we're very passionate at UbiQD to be working on a portion of this problem. And it relates to solar. So solar is an awesome carbon-free source of electricity and takes advantage of the relatively free and almost infinitely abundant energy source in our solar system, at least, which is the sun. And it's really in those urban settings where you have the high concentration of people and buildings that you have the highest demand for electricity. And so you'd like to be able to generate electricity there where it's needed, because there's losses associated with transmitting electricity and costs associated with transmitting electricity. So you should be trying to generate it close to where it's going to be used, and that's in a city. But if you can just take a look at a picture of any city, like here's Austin, Texas, for example, you'll note that there is not really any space available to put solar cells. On the rooftops of these buildings, there are leisure spaces and HVAC systems, and down the sides of the buildings, you have windows. And the real estate is very valuable in a city, so there's just not a cost-effective way to actually deploy solar in an urban setting. And at the same time, there's a huge trend that's been going on for really hundreds of years of humans living increasingly in cities, also known as urbanization. And it's correlated also with the rise in electricity prices, in particular in urban settings. So what I'm showing here in the main figure is just the percentage of populations in the world and in various countries living near or in a city. And you can see how on the right side, in the most developed countries like Japan or the United States, you'll find that more than 80% of the population actually lives in a city. And then on the inset, you'll see that the price of electricity in New York City is nearly double the price of electricity across the entire country. And that has to do with the demand being high and the supply of energy being low. So a solution to that problem would be, well, we should just generate electricity in the city and take advantage of the free solar resource if possible. And so the way to do that, at least our approach, is to convert those windows, all of that glass that you see in cities, to power source, basically a solar cell, but it needs to be transparent if it's going to be acceptable as a window material. So what we do is we tint the glass with quantum dots. The quantum dots are fluorescent. The light that they emit is effectively trapped in the glass. About 70% of the light can be trapped in the glass just by total internal reflection. And then that light gets guided to the edges where you put small solar cells around the perimeter of the glass, hidden out of view, which generates the electricity. This is called a luminescent solar concentrator, which isn't a new concept. So luminescent solar concentrators, the idea has been around for more than 40 years. But luminescent concentrators weren't able to actually make it commercially, primarily because of the lack of a proper fluorophore, a luminescent material. And with our quantum dots, we think that we've solved that problem, and I'll tell you more about that from here on out. So another thing to note a little bit that's different about our approach, in addition to the fact that we're using these unique quantum dots, we have a laminated glass solution. So in our market research, we've realized that glass is the only acceptable window material in the marketplace. And there's a number of reasons for that. But you can just kind of, probably isn't hard to agree with me just based on the fact that you don't see plastic windows. We can certainly make plexiglass, at large scales, but it's not used in windows for a number of reasons. And similarly, coatings on glass are also not very common. You may have a window tint in your car that has a plastic coating, but very rarely would you find a plastic coating on a facade of a building. And so our approach is to put quantum dots into the inner layer of laminated glass. And laminated glass is 2 sheets of glass with a polymer in between. And this is very commonly known in car windshields because it's used for basically safety reasons. So the windshield, when it breaks, it doesn't just fall apart, it actually holds together. And laminated glass is common, historically is common in places where you have risk of windows breaking. So high-rise buildings, or in hurricane zones or earthquake zones. But increasingly, laminated glass is now being used for other reasons, like sound dampening, or just generally for safety. And in some parts of the world, it's required by code. Like in Europe, all overhead glass has to be laminated glass. And in certain parts of the world, for other reasons, it's required. So it's a common approach for glass for other reasons. And now we're leveraging this to deploy quantum dots, because you can't put quantum dots easily into the glass, but we know how to put them into polymers. And so if we can just put them into that middle layer between 2 sheets of glass, well, you've got a nice monolithic, basically piece of glass that can be integrated into a window relatively easily. And so this does work quite well, actually. So we've done this with various kinds of glass, and you can see that concentration effect. And I'm showing here some visible emitting quantum dots, but generally we use near-infrared quantum dots for our windows. That will give you the best performance. And then at the edge, you can put those small solar cells, like I mentioned, and this isn't terribly difficult. You can source kind of any size and shape of solar cells these days. And we just basically stick them right there on the edge and then solder them together. And you can get, this is a square foot window that's outputting in the sunlight about 31 volts. When you've added those up in series, you can get higher voltages, and that can be useful for integration into the grid or powering various devices. So we do spend a lot of time on that edge. As you can imagine, that's an important part of it. You have to have good edge quality. What you can see there on the left is a polished edge laminate where you have that sort of dark middle layer that's what's containing our quantum dots, and then the 2 sheets of glass sandwiching that. And then we can attach the cells around the edge, and if you do this just right, you can sort of not even have to have any wires there. You just directly solder one cell to another cell, and it works quite well. That's for the single pane of glass. And so I should note that there are some special considerations and challenges as you go to make a double pane window like you see on the far right. So you have to have basically a proper spacer material there and sealant, and the edge becomes, it can become kind of delicate when you've got those solar cells there. So there are some considerations there, which I won't get into, but otherwise, you know, it's pretty straightforward how you can make a solar window with this approach. And we are doing this now up to about a square meter or about 10 square feet. And that's getting into the regime where you can start deploying it into actual buildings. And we're also doing that now. We've already deployed some of our first glass for pilot projects, and we're doing several more ongoing at this very moment. And just to sort of summarize what the excitement around this approach is, using quantum dots and luminescent solar concentrators in general, but also our laminated glass approach, it's basically a drop-in solution. So the idea is that we want to fit directly into the conventional way that windows are manufactured. This is way more acceptable to the industry than, say, completely revisiting the whole way that you'd make windows. So it's a seamless integrated approach. The cost is quite a bit lower than if you tried to make a very thin solar cell on a piece of glass, like in a clean room, which most of the other companies that are doing solar windows are trying to do. And that gives us a fast payback time. You know, it depends on the performance, which we also have. And so that makes it an affordable approach that has a reasonable return on investment for the customer. And then lastly, our aesthetics are unparalleled. There's no lines. Typically a solar window with a solar cell on the glass would have a crosshatch pattern for making contact to the individual cells. We don't have any of those issues, and we can also make a variety of different colors, which gives the architect a tunability that they really appreciate. And most of the time, they actually don't want to have a colored window. What they want is, you know, something that looks, you know, like a building would, like you expect a building to look. A color neutral or even a bluish gray color is preferred by architects for glass. And it's really going to be unacceptable to compromise aesthetics. It's a little bit disappointing from a technical standpoint that aesthetics matters so much, maybe even more so than performance. But it's just something we're going to have to accept in this market. And I've got this picture here of one of my favorite buildings in the world, the Maha Nakhon building in Bangkok, Thailand, which has this sort of pixelated glass structure. But I love it because it's all glass. And you can kind of get a sense of the architects are putting aesthetics maybe a little bit ahead of the function. Having this sort of pattern on the glass is probably not ideal for necessarily occupancy maximization, but just goes to show that aesthetics really is king when it comes to buildings. And so, like I mentioned, color is a big part of that. And one of the things we've been working hard on in recent years was how to balance out the color. If you just take our near-infrared quantum dots, they perform very well, but the glass, depending on the lighting and what's behind it, will appear somewhat brown. And architects will tell you that this would have been very popular in like the 80s when bronze was the color of the day, but not anymore. Nowadays, architects want more of a gray, true gray color, a neutral color. So we've purchased quite a bit of commercial glass, and you can see this green curve on the left as an example of that, where this absorption is actually stronger on the red side than it is on the blue, and that makes it look a little bit bluish gray. And so the way that one way that you can actually address this with the brown material is by adding an absorber on the red side. So basically a dye that looks blue or something that makes a blue color would be a red absorber. And by adding that to a brown, you basically balance out the color. And so you can see here, just going from unmodified to the increasingly adding the blue dye, you can get to a blue color fairly easily. So this does compromise performance a bit, but you'll have to stay tuned for the manuscript, which is under review now, to get the full story on that. Another approach to optimizing the aesthetics is to think about the visible light transmission. And so basically a darker tint or a lighter tint. And architects want to be able to adjust that. By adding more dots to the single layer, you can run into solubility issues. So the dots can start to crash out basically in the polymer, and you get a hazy waveguide, which is not very effective for generating electricity. So a solution to that problem is to make multiple interlayers. And so we have the same paper that I just mentioned under review now, where we looked at that. We made up to 5 interlayers stacked on top of each other, and you can see that the VLT, the light transmission does drop, and we can tune it over that range that architects care about. And at the same time, the absorption goes up of the device, so the performance should also go up. And we do see that, but it's nonlinear. So the internal quantum efficiency actually drops as you keep adding interlayers due to some effects that we discuss in the manuscript. But you do get an external efficiency improvement. So by adding absorption, you get better performance, but at a nonlinear rate relative to the absorption. Now, as you can imagine, having all of this glass there as a waveguide makes the glass very important as well. So the quality of the glass is critical, and also for the aesthetics. So normally, you know, having a better quality glass would mean it's a more clear glass. A lower quality glass might be a little bit greenish, is what's common, and that's due to iron absorption in the glass. Iron is added through the float process to make it manufacturable. But you can purchase low iron or even no iron float glass nowadays. But even within those categories, there's widely varying properties. And it's just showing here that one low iron float glass is not equivalent to another low iron float glass, which has a big effect on the performance. It could be a 50% difference as you scale up to a square meter, and how the quality of that glass plays a role. And again, this will be in the manuscript that's about to be released. So kind of putting it all together with all of our different advancements and innovations, we've been able to achieve a record efficiency for luminescent solar concentrators that was certified by a third party, specifically at the National Renewable Energy Laboratory. You can see the data here. The record champion that we got certified was around 3.5%, which is about 35 watts per square meter in direct sunlight. And then you can see on the right that part of the way we got there was by adding absorption, by adding these additional interlayers. And that gives you more full absorption in the spectrum. And so that gives you more current, essentially, in the final device. Of course, it's not going to be very useful if these degrade quickly in the sun. And so it's something we've worked a lot on. The laminated glass approach actually helps you out significantly in this regard, because the glass is a very good way to protect the quantum dot interlayer. But just to show you the kind of testing that we do, we take high intensity blue or UV light and shine it on the samples and measure the performance of the devices or the luminescence in real time. And I'm just showing here U.S. Senator Tom Udall, one of our systems that did this, that does this. You can see how intense that blue light is. And at about 5 times the intensity of blue light that's in the sun, at 450 nanometers, you can see that there's essentially no change in the light, in the performance, of the device over these hundreds of hours. And we've actually gone out to 3,000 hours in some tests, but I wanted to show one of our most recent scans here. And I believe this data will be in the supporting information of the paper that's about to come out. So that wraps up the story I wanted to tell about our windows. And just with the last few minutes, I was going to mention that we also do a couple other things. We have a large effort at the company on using our luminescent materials in greenhouses, not to generate electricity, but to generate crops, to generate tomatoes and cucumbers and that sort of thing. We have a brand for that called UbiGrow. You can go to the website ubigrow.com or just look us up on social media if you'd like to learn more. But UbiGrow is essentially how we describe it as a layer of light that helps plants. It uses fluorescence to create a more optimal greenhouse spectrum. And that's by converting colors that are underutilized to colors that are more efficient. And the most efficient color for photosynthesis is actually around 600 nanometers, this orange color. So we take that, we put it up above the plants in a greenhouse, and we've seen even higher than this number, more than 20% yield improvement of tomatoes in this case. This is a full season trial, large trial with actual commercial plants. And we're doing this all over the world now. We have trials in Canada, the United States, the Netherlands, and I thought it might be worth mentioning that we actually have an ongoing project in South Korea. I can't say specifically where it is at this point, but we do have some of our film deployed in South Korea right now. And it's exciting to the industry. They've described this as something that they've been waiting for, and that this has stirred up quite a bit of interest And it's a very stunning thing to see in a greenhouse, that glowing orange roof that our product generates. So just wrapping up here, I really can't take the credit. I've got an awesome team. We're based in Los Alamos, New Mexico. We were spun out of Los Alamos National Laboratory. A number of us, including myself, were postdocs. We've got 15 full-time employees. About half of them have PhDs. We like to have fun. We work hard, play hard. And we are hiring right now. So if you're interested in a job, particularly if you're in the United States or eligible to work in the United States, please do reach out to me, because we're looking to expand our quantum dot development team and application development team. So that's it. If you would like to reach out to me, I've got my phone number and email address here on this final slide. I'd be more than happy to take your questions that way, since we couldn't do it live. And I just wanted to also, again, thank the National Science Foundation for their continued support of our company and of the development of this technology. So with that, I will say thank you again, and see you soon.